Have you ever seen shooting stars? To me, are one of the most spectacular events when looking at the sky. Every August, I gather family and friends to watch them. Hundreds of meteors per hour streaking through the Earth's atmosphere, burning up and producing a brief but dazzling display of light. These events are mesmerizing, suddenly appearing above your head and zipping across the sky. And the longer you look up, the higher the odds of spotting one. And how fulfilling is when you finally see it. I love it. But they last only a few seconds. And let's be honest, the chance of seeing them isn't always that high. Not only due to bad weather or light pollution, sometimes you just miss them. You might have been distracted or simply looking at the wrong part of the sky. How frustrating, huh? Especially if the person close to you have seen plenty. But this feeling of missing out, the feeling of looking up at the sky and knowing that you missed something, is very similar to the feeling of looking into a microscope, searching for the smallest molecule, only to realize that you miss it as it moves and passes you by. For instance, right now, in your brain cell, synaptic proteins, a specific type of molecules, are appearing and disappearing, like shooting stars in the sky. And the study of these fleeting molecular events, as waiting for shooting stars, require patience, focus, and a bit of luck. The molecules are there, interacting, assembling, disassembling, but they're too elusive, out of sight or too quick to capture. This challenge, however, is what drives my research. As a scientist, I've spent years building microscopes to see the invisible at the molecular scale. We assemble mirrors and colorful light sources to illuminate molecules of different kinds, which are often made fluorescent, meaning that they glow when you shine light on them. But still, how you capture the life of this molecule, if it happens as fast as the shooting stars, and then randomly as the shooting stars, and it lasts as brief as the shooting stars? Well, I first realized that we should look for hints in your sample that would tell us where to look. For example, if you're interested in brain activity, changes in calcium concentration are excellent tools. Neuroscientists have been using calcium imaging to show how brain cells connect, form circuits which underlie our behavior. But since calcium transients happen really fast, 1,000 to 100 times faster than a second, very low resolution but fast microscopes are used to capture them. So I thought, why don't we use this system just to monitor our sample comprehensively, to learn where to look, where something interesting is going to happen. In the example of the shooting stars, this would mean to have a system that is fast enough to monitor all the portions of the sky at the same time, so that you would know where shooting stars is going to appear. And then you can position your head in that direction and film the event from start to an end. Coming back to microscopy, this would mean that we would look for calcium spike within your brain cell, and when a spike is happening, then we would start operating our favorite high-resolution optical instrument to film the event. So an event trigger observation, where the initial hint is calcium, but the event that you actually want to monitor is the relocation of synaptic protein during brain activity. And this is what we constructed. Together with the PhD students in my lab, we built a system that is smart and capable of decision-making. We integrated the optics of two different systems. One really fast to monitor your sample, and the other one operating at high precision. Basically, two microscopes in one. You might wonder why. Why do I need to do two in one? I could have just analyzed my sample first in the very fast microscope, annotate the position, and then transported it to the high resolution one and capture a movie. Well, time is crucial, and we humans are not that fast. Not in transporting sample, and not even in clicking a button to change the modality of operation, for example, from low resolution to high resolution. But luckily, computers are fast. They can compute images and react in a time scale that is compatible or even faster than molecular motion, simply by interchanging electric signals. And this is why we made the system, or the two systems, communicating autonomously. A real-time image analysis of sample image will provide answer to the hardware, which will decide to operate fast and fuzzy or precise. So we solved the problem of speed and randomness of the event. But you might wonder, how about high precision? I keep talking about high precision, but can actually a light microscope explore the molecular world? Well, as the name suggests, it's very good to explore the microscopic world. But when you start zooming in and zooming in, at some point, everything is blurred. You can't just exchange lenses as you would do in photography to zoom in into something interesting. It doesn't work. At the molecular scale, everything is blurred. But since a few decades, we understood that we have to think about the contrast method. If we use a particular kind of glowing molecule, which act like a light switch, meaning that you can turn them on and off, but with light instead of your finger, you can enhance the ability of a microscope, a light microscope, to look at the smaller scale. And this idea indeed was awarded with Nobel Prize in Chemistry in 2014, because it allows new and very precise observation. We can now explore length scale that were previously accessible only to an electron microscope. And this is cool, because light, unlike electron radiation, is not that damaging. So you can look at live a moving sample. But, there is always a but. It turned out that these systems are typically bulky, slow, and difficult to operate, posing big challenges for imaging scientists, which often ended up compromising the ability of capturing motion and focus on snapshot. But I didn't want to go this way. I wanted to capture the life of the molecule. I wanted to make movies, not still. And this is why we make the system smart and event trigger. So now we set an automated scheme of command so that we can monitor our brain cell comprehensively, many synapses at the same time, and spot for a calcium spike. And when we observe them, in a time windows accessible to computer but not to human, we can switch on the high resolution modality, a capture object as small as a synaptic vesicle, a few tenths of nanometer, in motion. You might wonder, why am I so obsessed with dynamics? And the reason is we can learn so much more about the system. We realized that since the recording of one of the first movies ever done, The Horse in Motion, 1878, experts at that time were debating on how the horse position is like during a gallop. Such a big animal, it might always have a leg touching the ground to hold itself. Well, it was disproved with this movie, which show a clear instant where all the four legs are above the ground. Now, you might not be interested in brain activity, but don't worry, calcium is not the only hint. We can look at local change in acidity of the environment, pH, or even change in shape of the sample or intensity, opening up new windows of observation in the interest of brain science, but also immunology or microbiology. We can look at cells, start bending their membranes and releasing vesicles, which is how cells communicate, or small organelle trafficking within the cell and start fusing, which is the foundation of how cells allocate resources. Imagine then what that could mean for research. Our event trigger system is just the beginning. With advances in AI and computational power, these tools will become even more intelligent. Compare the development from the movie of The Horse in Motion to the latest blockbuster movie today, and then think about what this technology can be capable of tomorrow. Capturing moments that we've never seen before, and they might change our understanding of biology and life itself. Just as we gaze up at the sky with wonder, hoping for a glimpse of something rare and magnificent, we look into our microscope, eager to witness at the hidden story of life unfolding at the molecular scale. Every observation might last an instant, but it has the potential to illuminate new paths in science, to unveil new truth, and to inspire us to keep studying the unknown. Thank you.